section 4.9 is on page 212. Talks about free mechanical vibrations. And if we look at a vector, given a vector, AB, if I point that vector, assume those are positive just for simplicity, nothing else. Assume this is AB, and the vector would really look like this. Oops, wrong line. This. Well, this is component A, this is component B, this is the angle it makes, and this right here is the magnitude of V. The book is going to call that capital A. That's what we need to find on the long run. And if I take the cosine of theta, that would be the adjacent over the hypotenuse, which indicate A is A times the cosine of theta. And if I take the sine of theta, that would be the opposite over the hypotenuse, which indicate that J component is A times the sine of that angle. Now, in general, our solutions are going to look something like this. If I have A cosine of omega t, plus B the sine of omega t, we would say y equal so A would be A cosine of theta and B would be A sine of theta, and this would be A cosine of theta cosine of omega t plus A the sine of theta sine of omega t, and this would mean that y equal A the cosine of, and either way we're going to take omega t minus theta in that order. Since cosine is even, you could swap those if you wish. That doesn't really matter. Where A is actually the square root of A squared plus B squared. Actually, it's right there. That's called the amplitude. And period is 2 pi divided by this omega, and we call this a quasi-period, and I'll tell you what that means in a minute. We have what's known as the frequency. Normally it is 1 over the period. Here it matches that as well, and this is called a quasi-frequency. And lastly, if we take this theta, that is inverse tangent of B over A. That depends on which quadrant you're in. There are a couple of exceptions. In this book, they don't like this. They use A the sine of omega t plus No biggie. That's fine. Since if you shift a sine or cosine, you end up with a... If you shift a cosine by pi over 2, you do get a sine, and vice versa. Now, theta is an issue because this book runs back and forth. Normally, we allow theta to be in these applications. We allow it to be between negative pi and pi. So we allow it to be in positive or negative rotation, the fastest possible route no matter where you are. This book kind of runs back and forth. Sometimes they stick with that, sometimes they don't. We're not going to disagree on that. Let's keep it the way we are. We have it. So when you find theta, make sure that it is between negative pi and positive pi, and that's fine. Now, a spring mass system can be expressed by external force is inertia, which is mass, times the second derivative, which is acceleration, and the damping, we call it B, and the stiffness is of the spring, which is given by K, where force equal force equal mg, and for the spring constant, we use Hooke's law, and we say normally it's F equal kx, but in this case they're using y for displacement, right? So this is mass, this is damping, and this is the spring stiffness. And to get the spring stiffness, we normally use Hooke's law, which is F equal, in this case, K times Y, and you want to figure out how stiff is this spring every time. And the damping force is actually V, and in every problem they're very specific. So if I look at problem number 2 and I proceed. Now this is provided, you really don't need to memorize that, and this is provided, you really don't need to memorize that. So on your test you will see those provided on your exam. I'm looking at page 220. And they jump straight for it. A 3 kilogram mass. The mass is 3 kilograms. Is attached to a spring with a stiffness. They give you the stiffness. Normally we find it in other books. In this book, they give it to us every time. The mass is displaced half a meter to the left of the equilibrium. So y of 0 to the left is negative, to the right is positive. And given a velocity of 2 meters per second to the right, the initial velocity is actually 2 meters per second to the right. The damping force is negligible, meaning the damping force is 0. Find the equation of the motion of the mass along with the amplitude, period, and frequency. How long after release does the mass pass through the equilibrium position? Alright, let's get the equation first. That's normally the key. If you find the equation, you're in good shape. So we know that, so m y double prime plus by prime plus ky equals external force. So in the external force, here, maybe I should put that up here, that will make it. So 3y double prime plus 0y prime, they said we have negligible damping force. K, they gave it to us to be 48. Again, in most books you have to find those, and the external force is 0. So pretty much I'm left with y double prime plus 16y equals 0. This is a homogeneous second order linear differential equation with constant coefficients. You let y equal e to the rt be the solution. Y prime is r e to the rt, and y double prime is r squared e to the rt. Most books use x, and you have to find the mass. They don't give you the mass, they just give you the weight, but you know, whatever works. In this case we get e to the rt times r squared plus 16 equal to 0. E to the rt cannot equal 0. It must be that r is plus or minus 4i, and that indicates that the general solution is y equal c sub 1, the cosine of 4t, plus c sub 2, the sine of 4t. Now, if I take y of 0, y of 0 is c1, and that's negative 1/2, there it is. And if I take y prime, that would be negative positive twice the sine of 4t plus 4c sub 2 the cosine of 4t. And if I take y prime of 0, that would be 4c sub 2, and that equals the 2, which indicates c sub 2 equals 1/2 as well. So negative 1/2 and positive 1/2. So y equals negative 1/2 the cosine of 4t plus 1/2 the sine of 4t. That would be the standard equation. Now, if I figure out what they want me to find the amplitude. The amplitude is, we said, the square root of this squared plus 1/2 squared. A is 1/4 plus 1/4, which is 1/2. So A is actually 1 over radical 2, which is radical 2 over 2. Got it. And if I look for, what else did they want? Find the amplitude we did. The period. Period is 2 pi divided by, and what would that be in this case? It's a 4 for both, right? That would be pi over 2. And if I look for natural frequency, that would be 2 over pi, basically the reciprocal of the period. And if I look for the angle, now this is something you should do. Again, this author sometimes does that, sometimes doesn't. If I move negative 1/2 and up 1/2, then the reference angle is the inverse tangent of 1/2 over 1/2 is 1, which is pi over 4. But since I am in the second quadrant, I'm going to say the angle is 3 pi over 4. Sometimes the book does that. Sometimes they say it's negative pi over 4. So let's just stick with this. And by doing so, then this is what I know. Y equals, and wouldn't that be radical 2 over 2? So I'm filling this part. The sine omega is a 4t, and the shift plus, so since it's shifted to the left, 3 pi over 4. That would be it. Now, once I get this equation, I could figure out the rest. How long after release does the mass pass through the equilibrium position? How fast after the release would this pass through equilibrium again. Basically, this passes equilibrium when it equals 0. Wouldn't that mean that sine equals 0 when the angle equals 0? So that's when t equals 3 pi over 16 seconds. That's how long it takes. Two more to go. Let me fix this one a bit nicer. Here we go. And here's another problem. Again, this author likes to provide everything, which is fine. At 20 kilogram mass, the mass is 20 kilograms. Stiffness of the spring. So again, this is always what you want. My double prime plus by prime plus ky equal f of t. You want to figure out what those are. They're given us k to be 200 newtons per meter. The damping constant for this system is 140 newtons seconds per meter. If the mass is pulled 25 centimeters, so we're going to pull this 25 centimeters, that means y of 0 is 25 centimeters. Now we have a couple of options. Since this is in meters and this is in meters, either convert the meters to centimeters or the other way around, and of course it's easier to go this way. So wouldn't you say that's 1/4 of a meter? You could multiply by 1 over 100, right? And any initial velocity. And given initial leftwards velocity of 1 meter per second. Okay, good. This one matches. It says, when will it return? When will it first return to its equilibrium position? So we start by finding the equation. Well, they gave us all the components, right? So they're telling us that we have 20y double prime plus 140y prime plus 200y, and they didn't say anything about external force. External force will simply give you a particular solution, so hopefully you're connecting all of these dots and you can see that. Well, if I divide by 20, this says y double prime plus 7y prime plus 10y equal to 0. Linear homogeneous equation with second order with constant coefficients. Let y equal e to the rt. Then y prime equal r e to the rt. And y double prime equals r squared e to the rt. So I'm looking at e to the rt times r squared plus 7r plus 10 equal to 0. E to the rt can never equal 0. It must be r plus 5r plus 2. So r equal a negative 5 and a negative 2. Well, sine and cosine are very easy to predict because of the graphs, you know. So this one is slightly different. C sub 1 e to the negative 5t plus c sub 2 e to the negative 2t. Now, if I use my initial conditions and say, alright, let's see. Y of 0. Well, y of 0 is c1 plus c2, and that is a 1/4. And y prime of 0. You take a derivative. Wouldn't that be negative 5c1 minus 2c2, and that equals, what did they say? That is 1/4 of a meter, and that is a negative 1. So in this case, I'm looking at 4c1 plus 4c2 equal a 1. If I multiply the bottom by a 2, I'll get negative 10c1 minus 4c2 equal a negative 2. If you add those, you will get negative 6c1 equal negative 1. c1 is 1/6. And if c1 is 1/6, I could say 1 over 6 plus c sub 2 equal 1/4. Clear the fractions. 2 plus 12c sub 2 equal 3. 12c sub 2 equal 1. So c sub 2 equal 1 divided by 12. So my actual equation for this is y equal c sub 1 over 6 e to the negative 5t plus 1 over 12 e to the negative 2t. Now this is not trig, sine, or cosine for you to set it equal to 0 and figure out how that works. In this case, you're trying to figure out when would this equal 0, and we have a problem. Theoretically, this could never equal 0. But we know as t approaches infinity, we know those will level to 0. But theoretically, you could never reach there. So it's not that simple. And one more. And here, we're dealing with a mass of 1/4 of a kilogram attached with a stiffness. They give us stiffness, and that is K equal 8 newtons. So again, it's my double prime plus by prime plus ky equal f of t, which is the external force. The damping constant is given to be 1/4 newtons seconds per meter. If the mass is moved to the left, y of 0 is 1 meters. All the units are matching. And released, y prime of 0 is 0. They didn't give it an initial velocity. What is the maximum displacement to the right that it could attain? Okay, I'll get to that in a minute. For now, let me just get the equation. And that would be what? 1/4 y double prime plus 8y prime plus 1/4 y equals 0. That would mean y double prime plus 32y prime plus y equal to 0. Again, a second order linear differential equation with constant coefficients. So I would let y equal e to the rt be a solution. Y prime will be r e to the rt, and y double prime will be r squared e to the rt. That would be e to the rt times r squared plus 32r plus 1 equal to 0. So e to the rt can never equal 0. It must be that r squared plus 32r plus half of the middle number, which is 16, and square it. Oh boy, that's a large number. Let me check. Okay, I noticed I fixed I'm like, wait, that's too big. Okay, I noticed I mixed those. My mistake. B is 1/4. You guys were supposed to help. And that's an 8. That makes this will make this 32y equals 0. So that's going to mean this is plus 1, plus r plus 1. So this is plus r 32. 30, yeah, there's no factor. There are no two factors of 32 that will add up to give you a 1. So half of 1 is 1/2 squared is 1/4. And that would mean r plus 1/2 squared equals negative, oh boy, here we go, for 128, 127 over 4. So I'm getting r to equal negative 1/2 plus or minus the square root of 127 over 2i, and my solution would be c sub 1 e to the negative t over 2 cosine of square root of 127 over 2t plus c sub 2 e to the negative t over 2, the sine of square root of 127 divided by 2t. And if I find those initial conditions, I would say y of 0 is c sub 1, 0, that's it. And that is 1. So that's a 1. And if I take a derivative, that would be the product rule. That would be, let's see, I'm taking e to the negative t over 2 times cosine of square root of 127 divided by 2t plus c sub 2, the sine of square root of 127 over 2t. So that will be the product rule. Derivative of the first times the second plus the first times the derivative of the second. That's negative square root of 127 over 2, the sine of square root of 127 over 2t. Now you could save yourself some time, because if you notice at 0, anything with a sine will go away, right? But no big deal. If you don't know what I'm talking about, just proceed and finish it up. Plus the square root of 127 over 2c sub 2, the cosine of square root of 127 over 2t. What is that dot? And if I take y prime of 0, I will get negative 1/2 times 1 plus 1 times square root of 127 over 2c sub 2, and that equals a 0. So that's simple. Move the negative 1/2 to the right, positive 1/2, the 2's cancel out. So I'll get c sub 2 to be 1 over the square root of 127. And positive or negative? Let me just think really quick. Yeah, positive. Okay, so I'll say y equals 1 times e to the negative t over 2 cosine of square root of 1. Y equals e to the negative t over 2 times the cosine of square root of 127 over 2t plus 1 over square root of 127, the sine of the square root of 127 over 2t. And that would be the equation. Now that's all we're gonna do. The rest of the work is a bit more intense than usual, so we'll just leave it like that, and that's why in your homework it says find the equation only, and I might ask for that on the exam as well. The homework is listed right there. Oh yeah, I never mentioned what a quasi, and let me tell you what that is really quick. What is a quasi period? Can't I write this as e to the negative t over 2? 3 and equal with an extra dash means equivalent. Can I write this here? Can't I combine find a and write this as a times the sine of omega t plus theta or phi? Since e to the negative t is multiplied by this number, whatever that number is, then wouldn't that be the amplitude? Doesn't a sine wave start at the origin, run up, come back down and up? This right here is called a quasi period, meaning it's compressed. It's supposed to be between, that's a full period. When you compress this and shifts down and compress this and pushes this up, that becomes a quasi-period. Your homework is on page 220. You're going to do number 1. Number 3, it has B equal 4 values, just do B. Do number 7. And number 9, just find me the equation.